So now we'll take a look at some examples in PSCAD and as well as Simulink. And for the first PSCAD example, we'll be looking at Inrush. And so what I'm going to do in this case is I'm going to take some data for a single phase transformer, and we'll use that for populating the PSCAD model. And what I've done is I've selected a 500 kVA transformer. This is single phase, so it's 7200 volts line to neutral on the high side. That would correspond to 12.47 kV line. And then on the secondary side, it's 277 volts, which would correspond to 480 line if it were Y connected. So we're assuming like a Y type of connection. The excitation current is 1% of rated current. And so the rated current in this case, if you take the 500 kVA divided by 7200 volts, that'll give you the actual current in amperes for the rating. And the excitation current would be 1% of that. We have a no load loss of 1140 watts. That's hysteresis and eddy current loss. We have a percent R of 0.7%, a percent X of 2.2%. And so in per unit, that would be 0.007 per unit ohms for the resistive part and 0.022 per unit ohms for the reactive portion of it. So then as far as what this relates to in the equivalent model, basically what we've got for the resistance and reactance is we've got this equivalent value where all this series impedance is referred to at the high side. What you'll see sometimes in these models is they ask you to break it down into a primary side versus a secondary side. And a real simple way of doing that would just simply be to divide by 2 in per unit and assume it's split 50-50. And then also, too, we're going to represent both a core model and a magnetizing reactance model. And so of particular interest is what's XM going to be. So anyway, given that we can do all these per unit transformations, we can work through and get these values in ohms or get these in per unit as needed. And then this is the table where I got these values from, and so this is a table from a distribution course textbook by Gannon. And basically what I did in this case is I went to the 500 kVA values. It looks like I didn't actually get these values all the way down, but this is the type of table I would have gotten these values from. And I think what I actually did in this case, yeah, I got those from the second page of this table, but this is just an example that kind of shows the format of this data. So anyway, what I did is I built a simple circuit in PSCAD. Basically has an excitation source to it, and then I've got the simple single phase transformer model. And what you can do in this case, if you want to check your model out, is you can go ahead and put meters in here. There's actually a combi meter you can put in here, which is going to give you PQ, voltage, a bunch of other quantities because you're taking both the current and the voltage measurement. And then I could either put a load on here or take the load off. So for the Inrush, we're looking at an unloaded sort of a case, but if I wanted to check my model, I might decide to put some load on here and just to see what I would get as far as voltage drop and everything else. So as far as populating all this, the way the model is broken down is you'd have one part of the model where you kind of look at it somewhat idealistically, where you don't have I guess I can say like a magnetizing branch associated with it. And then what you're going to do is you're going to basically add in this core model, and you'll put that in a second set of settings when you're doing the saturation. And so what I do in this case is when I load in the parameters, I'm putting in the kVA rating, or in this case is 0.5 MVA. I'm just putting in the leakage, and the leakage reactance in is as far as per unit values and putting copper losses in terms of per unit values. These eddy current losses, I don't have the calculations here, but they would correspond to the no load loss. You see what I'm doing here is I'm specifying the ideal transformer model, so I've got to go to this next set of inputs in order to put the core model in. And then I'm specifying the voltages on the high side and the low side. Again, these are aligned to neutral values. And then as far as the saturation part, as I mentioned before, since this is the classic model in PSCAD, then what's happening here is it's representing the saturation effect by putting a current source in here. So basically this is kind of like an add-on which gives us what this additional current would be when this model goes into saturation. And other things you would put in here is you would put like an air core reactance in here. So basically this is kind of modeling the saturation part of the curve. And it's a very simplistic model where basically as far as when the saturation occurs, it kind of waits until you get up to 1.2 per unit volts. And then what it would do is it would then model the saturation using this air core reactance. So it's actually kind of like a two-piece curve if you want to think about it that way. Something else that's also has in here, it has like an inrush time delay. So this is the amount of time that you're going to see the inrush active. And so eventually it's going to damp out, and this is what this is doing, is kind of representing the damping. So let me go ahead and pull over the PSCAD model for this. And so here's the PSCAD model in this case. And you can see what I'm doing is I'm setting up the transformer parameters as I just talked about here. So I've got the saturation loaded in. And then when I run this, what it's doing is just simply energizing this core right here. I don't have the load switched into the circuit in this particular case, or I think it's, let me just check here. Yeah, let's open it up. I thought it was open. Let's just take it out. It shouldn't really make any difference. So anyway, when I run this, then this is what I'm going to be getting for the results. You could see that as far as the inrush, that the current starts really kind of high. In steady state it would be 0.1, but here at these very high values it jumps up all the way to 0.5. And then you can see what effect this has on the voltage, because the fact that I have this high current with a lot of harmonics means I get a drop across the transformer, which is going to introduce harmonics into my voltage. And if I want to see in a little bit more detail what's going on here with this current, I can always change the scale on this, and I could look at less cycles of the input current. So let's change this to 0.05, let's say. And what I can see in this case is the current goes positive, and then when we hit the saturation it just suddenly jumps up, and then it drops back down again, and then we basically kind of get this asymmetric glitch in the current corresponding to when the transformer goes into saturation. So not really elegant in this case. I mean, if you could play around with this a little bit more, you might get something that might look a little bit more realistic, but that's basically how this particular model works. And it's sort of up to you to kind of play around with the air core reactance and you know, come up with the right parameters as far as modeling this saturation effect. You can also do this, let's see, You can also do the same thing in Simulink. And so here's an example of a Simulink test circuit as part of one of the examples that came with Simulink. Here's the transformer model. You can see we're basically energizing it from a source. This obviously is more of a transmission transformer instead of the distribution case that I had before. And then what they're doing is they're using the Fourier analysis capability to calculate specific harmonics associated with the current part of the inrush. So this shows the transformer setup in this case. If I would double click on the transformer model, basically what I can do is I can put in the power rating. I could put in the winding 1 and 2 parameters, and note what's happening in this particular case is this is a 3-winding transformer, and what you're actually doing is you're putting in different resistances and reactances per winding. So if I had a 2-winding transformer, I would put half of it on winding 1 and half of it on winding 2. You can go ahead and you can put in a magnetizing resistance if you want to. This is simply the core loss model. And then to represent the saturation, what I'm doing is I'm putting in some points from a current versus a flux curve, and then basically this is all in per unit. So basically we're assuming that the saturation is starting to occur after 1.2 basically, and then we shift to a different curve. So it's not a real detailed model here either. But anyway, when you run this model, then you also see that you've got the current jumping up due to the inrush, and it jumps up to a really high value. And you would also see during the inrush that you have some distortion on here for the voltages as well. You can also see the output from the Fourier analysis looking at the fourth harmonic component. And again, if you're using a relay here and you want to have like a harmonic restraint to keep the overcurrent from tripping, you could actually look at something like the second or the fourth harmonic current, and you can use this to keep the relay from actually tripping out then. So as far as what this would look like in Simulink, again, I mean, this shows the actual simulation in this case. You can go in and you could take a look at the details of the model here. Thing I didn't show you before is it didn't show you how you can actually set up the winding configuration. And so what you can do for the 3-phase model is you can actually select like whether you have like a Y ground or ungrounded Y or delta connected winding. You can have different phase shifts depending on whether it's a D1 or a D11. Another thing you can do here too in the Simulink model is you can specify what you have for the core model. Now in this case, this is 3 single-phase transformers, and so this would be kind of the default in PSCAD, right? But then you could also model different types of cores, and so you can have a 3-limb core, which is what we call a core type, or you can have a 5-limb core, which is what we call a shell type. And then what it's going to do, it's going to make certain assumptions in here, you know, as far as coming up with the equivalent cross-coupling inductances. So anyway, this is what I mentioned before. This is where you can actually set up the parameters, and you could actually put a little bit more detail in here on the saturation characteristics. If you want to get a little bit more detail, you can also set up the initial fluxes, and so this is going to be due to whatever we had from the last time this device right here was switched. And then once you have all this stuff loaded in for the transformer, then if you go ahead and run this, then we could use the scope to take a look at some of the output results. So it's compiling this right now, and it's going to run it. So again, when the switch closes, Basically all these switch elements, these three phases of the switch would all close at the same time. What that would do is that would give us different points on wave. So that's why one phase is always worse than the other two phases. Because as you know, the worst case would be when we're kind of close to a zero crossing on the voltage. And so you can see one of the phases gives us the most current inrush, and then we get lesser current inrush on the other two phases because all these voltages are going to be off by 120 degrees. But you can see after a period of time, depending on how much damping you have, that this inrush current starts to disappear once we get into the simulation. Another case that we can take a look at is we can take a look at ferroresonance. In this case I have here is one of the cookbook examples that they have for PSCAD. PSCAD has a number of different examples, and so they have this simulation cookbook where it goes through different types of studies, and this one is in one of these examples on the site. And so what they're doing in this case is they have a power system, they have a transmission line. At the end of the transmission line they have a distribution transformer, and then they have some small load. And so what you're doing is you're energizing the one side of this transmission line. This transmission line is going to have some capacitance with it as well. And so the capacitance is going to interact with the nonlinear magnetizing inductance on the distribution transformer. And what you're going to see is you're going to see the potential for ferroresonance in this case. One thing you'll notice on here, which we haven't done in class yet, but this is making use of what we call three-phase block connections. And so instead of drawing everything out in three-phase detail and having wires for phases A, B, and C, you basically, if you have these three-phase blocks, can connect these up directly and then not have to worry about all the details of the A, B, and C phase. This is just simply three-phase blocks in this case. So anyway, for the transformer model, what we're using in this case is we're using the classical model for PSCAD. Again, we put in the rating information. We have to put in the windings types if it's delta or Y connected. And you note on the high voltage side, we're putting in a delta connection. I said the delta connection is more susceptible to ferroresonance because if a switch sticks, if we have an unbalanced situation, then we can have a path to ground involving one leg of the transformer and a capacitance of that line. And so what we're doing in this case is we're putting in these parameters for modeling the inrush characteristics. And again, I've got an air core reactance in here. I'm putting in a magnetizing reactance. Something else you see in this model too, which we'll get into the next section, is we've got the transmission line model. And so this is kind of the way you would represent this in PSCAD is you actually can show the spacing between the conductors, and it'll go through and it'll calculate the different impedances and capacitance, which we'll talk about next lecture. And then when you run the simulation, when the switching occurs at 0.3 seconds, and you can see after this that on the primary side you see these really erratic voltages that take place. So what's interesting about this is going to be a function of the damping. If we had more damping in the circuit, this isn't going to happen. So in this initial circuit we do have 0.25 megawatts of load, which might seem like a lot, but in the scheme of things for transmission level this isn't much load. So this load adds resistance into the circuit. And if we go ahead and we put some additional damping in here, what this does is going to change the characteristics enough where we don't see this ferroresonance effect anymore. Basically, we've lost a phase on the circuit. That's true. It's going to be unbalanced, but at least we don't see the ferroresonant chaotic operation that we did when we had the less loading on the circuit. So basically when where you're susceptible to ferroresonance is we're doing the switching of unloaded devices. If you put a little bit more loading on there, you can reduce the possibility that this ferroresonance is going to be occurring. So I'll have all these